Solubility equilibrium is going to be what the purpose of this lesson is, and solubility equilibrium is going to be the second type of equilibrium that we are doing in AP Chem. So let's get going. So solubility means you're going to have to know your solubility rules. The solubility equilibrium, the good news is it's very simple. The bad news is you've got to remember all those rules we talked about in pre-AP and again earlier this year. When we talk about something being insoluble, we're actually lying to you a little bit because it's actually a tiny bit soluble. And, excuse me, that's what this equilibrium is going to be about, okay? So, really and truly, when we say something's insoluble, it's just that it has such a low saturation point that it seems like nothing is soluble when, in fact, there's a teeny tiny bit that is. And so that's what we're going to be working problems with for this chapter. So, slightly soluble salts establish a dynamic equilibrium. Remember, that means equal amounts are going into solution as are precipitating. And so we're going to use the formation of silver chloride as an example when we have AgNO3 and NaCl adding together. So when the solid is first added to the water, no ions are initially present. But as the dissolving process proceeds, the concentration of ions increases until that equilibrium is established. And of course, that's when we reach a saturated solution. When we're talking about KSP, we're only going to be talking about the ions that will appear in solution because remember, we don't have solids or liquids that appear in the expression. So it's going to be a little bit easier calculations because you will not have a denominator. You'll just have a numerator. So here is an example for our AgCl that we were talking about. And so the way that we would write that KSP value once the AgCl is dissociated is we would say KSP is equal to Ag plus and Cl minus. Again, just like in equilibrium last chapter, you're going to raise the concentrations to the power that is their coefficients. And in this case, of course, it's both 1. So let's continue on. These are some values of solubility product constants. These are values that are published and you look up. They'll either, usually if it's a problem on the AP exam, they'll give it for you that particular thing. But in case they were to give you a snippet, you'd know how to look that up. For instance, we were just looking at silver chloride, and it is right here. And so we would see that that constant is 1.8 times 10 to the negative 10. And then we could look that up and say that's what our solubility product constant is equal to. So let's practice writing this for a couple of these. We have the Kp expression for each of the following. So because we have this 2 right here, when we write that, we're going to say calcium 2 plus, and then we're going to say F minus raised to the 2. And then if we were to go look up that value, we would see that according to this chart, it is, find it on there, calcium fluoride is 3.4 times 10 to the negative 11. And again, no units on our K values. For silver chromate, we would say is equal to Ag plus and squared, or to the second power. And then the chromate, O4, 2 minus. And then when we look that value up, find silver chromate, we see that it is 1.1 times 10 to the negative 12. And then the KSP for, that is calcium oxalate, would be calcium, and then the oxalate. And of course these are concentrations because they're ions. Oops, that's 2 minus. Sorry, I forgot the 2 minus. And then when we look that one up, that would look like that is 2.3 times 10 to the negative 9. So that's how you write the KP, or KSP, excuse me, expressions for solids. So now, most of the time we're going to be determining KSP from experimental measurements. Usually they are determined by laboratory using spectroscopic methods. And now where we're going to have to make sure we understand is our stoichiometry. So let's get going. So here is an example right here of lead 2 chloride dissolves to a slight extent in water according to this equation. Calculate the KSP. If the lead ion concentration, so they're not giving you KSP this time, is 1.62 times 10 to the negative 2 molarity, okay? So if the lead's concentration, because it says the lead's concentration is this, that means the chlorine concentration is twice that, and that's because of this right here. And honestly, that's probably the toughest concept or the biggest mistake that kids make when they're doing this, is they had to double the concentration and you still have to square it because of the 2 right here. And that is probably the biggest hurdle or the biggest mistake that kids make, is they forget to double it. Because remember, way back in Chem 1, and this gave kids a struggle, when you dissociate this PbCl2, you will have twice the concentration of chlorine whenever you do that because of the stoichiometry of the formula. And so, of course, when you put those into the calculator and calculate, you get that the KSP value is 1.7 times 10 to the negative 5. And if we look back at our chart, we see that PbCl2 is 1.6 times 10 to the negative 5, so we're pretty close to that. And so it's a way to check ourselves if you have a chart available to you. With your homework you will, but on the AP exam you might not. You just have to go with it. So let's practice one on our own with copper 1 bromide. Has a measured solubility of 2.0 times 10 to the negative 4. Calculate its KSP value. So we'll start by writing our KSP expression. And we're good to go here on that. Oops, not 2 plus. It's just a habit. Sorry. We usually have 2 plus. It's the most common form. And then bromide. Okay. So it gave us our concentration right here. So we're going to just plug that in and say 2.0 times 10 to the negative 4 times 2.0 times 10 to the negative 4. And we get our KSP value to be 4.0 times 10 to the negative 8. And of course, that's a lot easier than the equilibrium we did for the last chapter. But don't worry, we're still going to see rice tables. I know you missed them. In this one we have calculate the KSP value for bismuth sulfide, which has a solubility of 1 times 10 to the negative 15. So in this one I want you to go ahead, and I should have done this on the last one and I apologize that I didn't, but I want us to get into the habit of going ahead and writing the dissociation. So we're going to have bismuth, which is a 3 plus, and we're going to get 2 of those, plus 3 sulfides, which is a 2 minus. Okay? So when we write our KSP, it's going to be bismuth raised to the 2nd power, and then sulfide raised to the 2nd power. Oops, excuse me, 3rd. I looked at that minus 2. 3rd power. Okay? Now we're going to plug this in. So we're going to take this 1.1 times 10 to the negative 15, and we're going to multiply it by the numbers that we have in front of that. So KSP for bismuth is going to be, we're just going to go ahead and write it like this so you get used to seeing it, 2 times 1.0 times 10 to the negative 15 raised to the 2nd power. That's pretty messy. Let's do that again. And then 3 times 1.0 times 10 to the negative 15 raised to the 3rd power. And then when we do all that math in our handy-dandy calculators, we should get 1.1 times 10 to the negative 73. Okay? So that very negative exponent is going to tell you that this is so marginally soluble. Okay? When you have a really, really high negative exponent, that means it's barely going to have anything dissolved into the solution. Now, we can also estimate the solubility from the KSP values. So relative solubilities can be compared, but you've got to be very, very careful. So you have to be only if you have the same ion to ion ratio. In other words, if you're comparing something that has 3 ions, you can only compare it to something else that has 3 ions also and look at their KSP values. Okay, so if I was going to compare calcium fluoride to, say, calcium bromide, I could look at their KSP values and look at their exponents and see whichever one is smaller would have less solubility. However, if I wanted to say calcium fluoride, against aluminum bromide, I couldn't compare those directly using their KSP values because they have different number of ions. One has 3, one has 4. So you have to be the same number of ions when you do that. Okay. Also, I want you to not forget that solubility changes with temperature. Generally, we've said in the past that with increasing temperature we increase solubility, but that's actually not always the case. Some substances are less soluble while they're hot, and then some are actually more soluble when they're cool. And so we have to keep that in mind. Okay, so let's go on and do our first example. So we have KSP value for copper 2 iodate, and they give us that, and it says calculated solubility at 25 degrees Celsius. Okay, so we have our KSP value, but we don't have our molarities or our concentration, so we're going to need, you guessed it, a rice table. So we're going to do our dissociation. So we're going to have copper iodate. Of course, that's a solid. And you honestly don't have to put that in there when you're doing this part. So we're going to have copper 2 plus 2 iodate. So here's our R, our initial change and equilibrium. So initially we have 0 and 0. Our change is 0, and this is going to be x, and this is going to be plus 2x. So at equilibrium, the reason this is 0 is because, I know you're thinking, why is it not x or whatever? Remember, it's a solid, so we're not having any values for that whatsoever. So at equilibrium, we have x and 2x. All right, so I'm going to give you a chance to catch up, and then because I didn't leave myself enough room, I'm going to need to erase that and give myself some more room. So then our KSP, of course, is going to be equal to copper 2 plus sorry about that, I had lost my Wi-Fi connection in the middle of the video. And then we have the iodate minus, and it's going to be raised to the 2. Okay, so we know that we had a KSP value of 1.4 times 10 to the negative 7 is equal to x for copper, and then 2x to the second power. So then we have 1.4 times 10 to the negative 7 is equal to 4x to the third. And then we want to divide both sides by 4. This is just simple algebra here. So then we have 3.5 times 10 to the negative 8 is equal to x cubed. And then, of course, x is going to be equal to the cubed root of 3.5 times 10 to the negative 8, which would bring us to well, the answer says 3.3 times 10 to the negative third, but for some reason I have 3.4 on my paper. And of course that is molarity, or you could write it out as moles per liter right here, and so that would be your answer. So much simpler math with this KSP value by the fact that we don't have anything on the reactant side showing up on the bottom. So now that brings us to common ions, the solubility and the common ion effect, and I think that got left out of, yeah. So let's look at that, and let's see, for some reason on this one, if you look at the KSP value, it's a little bit different than what's in the chart, and I'm not sure why. It might have been an old chart or a new chart, but because our answer is already listed for us and we don't want to confuse ourselves, we're going to go ahead and just use that value. Plus, on an AP exam, you would use whatever value, or in a problem, you use whatever value is given to you. Don't go ahead and change that. Okay? So, we're going to need our rice table, so let's start with that. CaF2 goes to Ca2 plus 2F minus. Okay, so there's our R, ICE, and then, of course, these are going to all be 0 because they're solid, so we don't care about them. And then at this point, they gave us this concentration right here, okay? And so this is going to be negligible or 0, whichever one you want to put. And they gave us the 0.025, and so this is just 0.025. Whoops, sorry, I don't know what's going on there. So this is just 0.025. It's not times 2 here. Okay, and the reason for that is they gave us this concentration right here, and there's only one ion, so the initial concentration is 0.025. Okay, so then when we have our change, we're going to have plus x and plus 2x. So at equilibrium, we have x, and then we have 0.025 plus 2x. Okay? So now we have our 4.0 times 10 to the negative 11. Our KSP value is equal to x. And they're going to have 0.025 plus 2x squared. Okay? Now, I'm going to show you something that's going to make life much easier. You can't always do this, but it's always a good idea to do this first and then you check. So, because we have a relatively large concentration in the 0.025, this 2x right here is going to make very little difference in the overall concentration. It's going to make very little difference. So, we can assume that it is negligible. And if you make that assumption, you must write that down. Say, assume negligible. Okay? And the rule is if it's within 5%. I don't know how to spell negligible, apparently. Nope, not another B. Not another G, it's a B. I'm trying to talk and write, and it's never good. That is spelled wrong. Just whatever. Negligible. I need to learn how to spell that, apparently. It did need a B. Okay, you assume negligible. This, when you assume this, it has to be within 5%. Okay? And we're going to check that when we get to the end, once we get our answer. Okay? So we're going to assume that's negligible and drop it off. So when we do that, it looks like this. Okay? I'm going to, if you're not caught up, pause because I'm about to erase and then continue pouring. Okay. So that brings us to the fact that we would have 4.0 times 10 to the negative 11 is equal to x. Okay, we can't drop that x because that's the only value we have. Plus 0.025 to the second power. So when we do that math, we get that x is approximately 6.4 times 10 to the negative 8 moles per liter. And when we check that, we see that that value is less than 5% than the original concentration of 0.25. So it's a good assumption. Okay. Now, if you get to it and it's more than 5%, then you're gonna have to go back in and put the x back in there because it's too much and it's not negligible anymore. But in this case, we're good to go, and it makes our life easier. I like being able to assume negligible. It's awesome because it makes our math easier. Okay, so that brings us to the reaction quotient, which is calculated the same way, just like in the last chapter. But this time, before we said if it was greater than K, it meant it was going to shift whatever and no shift and all this. This is different, okay? This is going to tell us whether a precipitation is going to happen, okay? So if the KSP is, if the KSP is less than or greater than or equal to, it's going to mean whether we precipitate or not. Okay, so in this first one, we say that Q is less than KSP. That means that the system is not at equilibrium. It's unsaturated. So no precipitate would form. No precipitate. Okay. If it's at equilibrium, it's right at saturated. So again, no precipitate would form. But if Q is greater than KSP, that means you are not at equilibrium, but that means you're supersaturated. Okay? So that means you will form a precipitant. Okay? So remember those terms from way back in Chem 1 where we have 3 types of solutions. We can have unsaturated, which means more stuff could dissolve. We have saturated, which means you've reached your maximum. And then, of course, supersaturated is where we'll do crystals and we'll form crystals. That's how they make, basically when you drink sweet iced tea, it's a supersaturated solution because they've heated it up, dissolved more sugar than they should, and then they cooled it back down so it tastes yummy. So, precipitation of insoluble salts. Okay? A couple of things. Metal-bearing ores, that's hard to say, okay? Metal-bearing ores often contain the metal in the form of an insoluble salt. And they form an insoluble salt, and to complicate matters, they often contain several metal salts. So usually when you have a metal ore, you don't just have, one thing, you have several. So you can dissolve the metal salts and selectively precipitate one metal at a time. All right, so determining precipitation conditions. So we're going to calculate Q here, and then we're going to compare. So we have a solution of cerium nitrate, and we have this right here, and it's added to this solution right here. And it wants to know, will the cerium nitrate form a precipitant? So we're going to do our calculations. So we're going to calculate for Q right here. And we have cerium 3+, and then nitrate, and it's going to be raised to the third. Okay? So it's given us our KSP value right here, so we're going to need to do that. Okay, so first thing we need to do is we need to figure out what our concentration of cerium is, because we've got 2 sources of it, so we're going to figure out our concentration of that. So the first one is we've got to find our so we have 0.75. And honestly, in this case, you can leave it in milliliters if you want to make your life easier and make it better, easier math. So we're going to just leave that in milliliters because we're going to have milliliters on the bottom to cancel that out. So we have 700 milliliters times the molarity, because remember, volume times molarity gives you moles. And we're going to divide by the new volume because we've added solution to that. So our new volume is 750 milliliters plus 300 milliliters. Okay. Now, just to recap, what I did here is I have number of moles from the original amount right here. Okay. But I'm adding 300 mils to the 750 mils. So I have to divide by the new volume to get the new molarity. And when I do that, I get 2.86 times 10 to the negative third molar. Okay? Now I need to do the same thing for the iodate. And we're going to do 0 and 0, so this is our initial, so we know that, because it's not our final concentration. So this time, I'm going to do 300 milliliters, because that's how much I have, times, I should have done this in another color so we could keep them separate. Sorry about that. And then we're going to divide by 750 milliliters plus the 300 milliliters. And the reason I can leave it in milliliters, just in case you're wondering why didn't I change it to liters, is because I'm canceling out units on the top and the bottom. and then I get 5.71 times 10 to the negative third. Okay, and so that's my concentration. So now I'm going to plug it in up here to see what my Q value is. So let's do a different color. So now we've got Q is equal to the cerium, which is 2.86 times 10 to the negative third. And we've got the iodate, which is 5.71 times 10 to the negative third raised to the third power. So I get a value of 5.32 times 10 to the negative 10. Okay? Now here's where I want to caution you. If you were working this problem out on the KSP, on the AP exam, you would actually need to state, don't just say, yes, a precipitant will form. You need to state, Q is greater than KSP, therefore, precipitate will form. It's very important that you say that. Okay? Because when we compared this value, 5.32, to 1.19, it is greater than, so we would get a precipitate. Okay? That was fun. You want to do another one? All right. This time we have a solution prepared by mixing 150 milliliters of some magnesium nitrate and 250 milliliters of some sodium fluoride. Calculate the concentration of magnesium and fluoride at equilibrium with solid MgF2. So we're going to need to do Q again. So first of all, we have to determine if a precipitate forms. And then this is a long problem, so settle in. This one's going to take us a while. Okay, so we know we're going to have to do Q, so let's write it up here. Q is going to be equal to magnesium 2 plus, and then F minus to the second power. All right, so first we're going to determine if precipitants form. So first, I'm going to say check. I'm going to do that for precipitant. Okay, so let's do our magnesium concentration. I'm having some trouble with the pen today. All right, so magnesium had 150 milliliters times the 1 times 10 to the negative 2 over 150 milliliters plus 250 milliliters for the new volume, and we get 0.00375. Again, if I'm going too fast, pause the video before I write the answers, but I'm pretty sure you know how to plug it in your calculator. So F minus concentration is going to be 250 milliliters times the concentration of the sodium fluoride, which is 1 times 10 to the negative 1, and then 150 plus 250, oops, 5 didn't come out, and that brings us to 0.0625 molar. So now we plug those values into that right there. So Q is going to be equal to 0.00375 times 0.0625 to the second power. So then that is equal to 1.46 times 10 to the negative 5. So Q is greater than K. So precipitant will form. Okay, so we know a precipitate will form. Okay? So that brings us to the next the next step. You're going to love this problem, by the way. I keep looking ahead and going, okay. So let's go to the next step. I'm going to wait just a second. I'm going to pause this to let y'all catch up in case I'm writing too fast, which I probably am. Okay, now that you have all that written down, now comes the fun part. We're going to actually have to do 2 rice tables, okay? So first we need to figure out, because we know that a precipitant forms, so we have to figure out when that precipitant forms, what are the concentrations at that time. So we're going to do the forward reaction, or I guess it would be the reverse reaction in this case. So we're going to look at it and say we have Mg, sorry, my phone. All right, sorry about that interruption. So we have Mg 2 plus is going to join up with 2 fluorines, and it's going to make MgF2. Okay, so this is our rice table. So initially when we have that, we have to calculate, remember when we're doing the rice table here, we got to have moles. So we're going to multiply this times this to get number of moles. And so when we do that, initially we have 0.0015 moles. And when we calculate this one right here, we get that we have 0.025 moles. So clearly we're going to run out, and this of course is 0 at this point. So clearly we're going to run out of the magnesium. So our change is going to be minus the 0.0015, because when I run out of that, I'm not going to be able to make any more, and minus 0.0015. So at equilibrium, I have 0, and then I have 0.022 moles. Okay? So I'm going to have to find the new concentration of this, which is basically how much leftover fluorine I have. So when I do that, I'm going to say 0.022 moles divided by the whole new volume, which is 250 plus 150. Okay, where were we? Sorry about the second interruption. So we have the number of moles divided by the new volume, which is going to be 400, so 0.4 liters. So our new molarity is 0.055. And that's just for the fluorine, because at this point we have no magnesium solution, or magnesium ions, okay? So now we can go to the next rice table. So here we go. I'm going to erase this, so if you don't have all this written down, pause it real quick before I erase it. All right. So now we are trying to be at equilibrium. So now we're going to do our normal rice table, which we have the magnesium fluoride breaking apart because we're at equilibrium. So we're going to have the 2F minus. Okay. So this is RiCe. So this, of course, these are all zeros, so you can just put a big 0 or just ignore it. And then we're going to have 0 here, and we have 0.055 molar here. Okay? And then this is going to be plus x, and this is going to be plus 2x. So that at equilibrium, we have x 0.055 plus 2x, just like we did earlier, because now we can get to that point. So now we're going to plug it in. We know that our KSP value is 6.49. 6.49. I just totally made that up. Actually, I think I just combined it. So we have 6.4 times 10 to the negative 9 is going to be equal to x for the magnesium, and 0.055 minus 2x squared. Okay, so we still have a relatively high concentration, so we are going to, I'm going to write this down, assume x is negligible. Okay, oh, better not abbreviate that. It looks like I'm saying negligible. Why can't I spell that? I need to go back to negligible. Okay. So we're going to assume that's negligible. So then we're going to do our math, and when we get all that done in there, I'm running out of room, so I'm going to trust that you can do the math of simple algebra. We will get that magnesium at equilibrium concentration is going to be 2.1 times 10 to the negative 6, which is going to be our x value, molarity, and fluorine is twice that because of the 2x, 5.50 times 10 to the negative 2. Oh, well, not twice that because we had to subtract. Not subtract, add. Oh, I'm so sorry. I'm having an issue today with all these interruptions. I apologize. So this was the 0.055 plus the 2x. Okay. All right. Hopefully you understood all that because that's a lot going on in that problem. And I think we are getting close to being done. Okay. So let's go on to the next slide. Oh, next part is solubility and the common ion effect. And that means experiments show that solubility of salt is always less if you have a common ion, okay? And that's because of Le Chatelier, remember him? Be reasonable and use approximations when you can. The pH can also affect solubility. You want to evaluate the equation to see which species would react with the addition of an acid or a base. So in this case, we have magnesium hydroxide. Would it be more soluble in an acid or a base, and why? Okay, so we have this right here. If we're looking at that, excuse me, if you're looking at that, you're going to say, okay, what's going on there? But if I'm adding this, well, I can't write? Sorry. If I'm adding this to an acid, okay, what's going to happen is the acid will react with that and remove the hydroxide, which would increase the solubility because then more would be able to dissolve or go into solution because I'm keep removing that to react with the acid. But if I was adding this to a base, the hydroxide doesn't really have anything to react with, and it saturates the solution quicker. So magnesium hydroxide would actually be more soluble in an acidic solution than in a basic solution. So that's an example of that. Solubility, ion separation and qualitative analysis. This is a section that is going to say how the basic chemistry of the ions works. It illustrates the principles of how they're applied in the laboratory. So in this case, we're going to have an aqueous solution of silver, lead, cadmium, and nickel. Okay, and you can come up with a plan of how to precipitate all those out. Okay, so if we look at the chart here, from the chart here, it kind of shows you the things that will precipitate out. For instance, if we are adding HCl to this, we know it would separate lead and silver, and then it takes you through that process underneath there. So after that, we would say, okay, so if we add HCl, we're going to precipitate out the lead and the silver, while the nickel and cadmium would stay in solution. And then we could separate the lead and silver precipitates by filtration. And then if we were to heat the solution, that would cause some of the lead chloride to dissolve. Filtering the hot sample will separate the lead from the silver, and then the solid would remain in the filter paper. In order to separate cadmium and nickel, we would precipitate with sulfur, and then we could use our KSP values to determine which ion will separate first, and that's what we're going to do. Okay? Now, on an AP exam, they might not be this complicated, but this is something you need to understand and know how to do. So here we go. This is a different example because we have copper, but we have a solution containing some copper and some lead, and then we're going to add some iodine to this solution. And so it wants to know, will the lead iodide or the copper iodide precipitate first? Okay? And then we're going to specify the concentration of iodine necessary to begin the precipitation of each salt. Okay? So if these had the same number of ions, we could just compare their KSP values and say, oh, this one's smaller, so this value is smaller, so it precipitate first. But we can't do that because we have 3 and 2. So we cannot do that when you have different number of ions. So we have our KSP, of course, for each one is going to be PB 2 plus, and then iodine to the second power, and then the KSP for copper is going to be copper and iodide. All right, so it gave us our KSP values, so we are going to compare that. So it gave us the concentration of the lead is 2 times 10 to the negative third, and the concentration for copper it gave us as 1 times 10 to the negative fourth. So it doesn't really matter which one we do first. We're just going to do lead first because I see it first right here. So for PbI2, we have 1.4 times 10 to the negative 8 KSP value is equal to, and we've got our value for lead, it's going to be equal to 2x squared. And the reason it's 2 is because when that dissociates, you get 2 right there. So when we do that math, we get that the iodide concentration needs to be 0.0013 molar required. And that's required to precipitate. So now let's do the same thing. We'll do it in a different color for the copper iodide. So same concept. We've got 5.3 times 10 to the negative 2 is equal to, and then it gave us a value of 1 times 10 to the negative 4, and then x. And when we calculate that, we get that the amount of iodide needed is 5.3 times 10 to the negative 8. So it is much, much smaller amount required, so we would say that the copper iodide will precipitate first, because we'll compare that value. So you're going to reach a concentration of 5.3 times 10 to the negative 8 much sooner than you would reach the one for iodide, which was 0.0013. So pretty simple calculation, but you got to know to double this 2x. That's probably usually what gets people right there. All right, solubility in complex ions. The formation of complex ions can often dissolve otherwise insoluble salts. These are just some tips to know. Often, as the complex ion forms, the solubility equilibrium shifts away from the solid, causing it to become more soluble. If sufficient ammonia is added to silver chloride, the latter can be dissolved, and it will dissolve as this complex ion, which is soluble. Okay, that is a significant improvement with regard to the solubility of AgCl normally. Okay, and so that's just to kind of let you know that that can happen. Things can improve your solubility. And that is the end, my friends. I know this is a long lesson, but I wanted you to have all the calculations. And so if you have questions, of course, you can come in for tutorials or ask during class. The end. Have a nice day.